How do you catch a flying skyscraper? Not metaphorically, literally. How do you snatch a 70-meter-tall, 250-ton rocket booster falling from space at hundreds of miles per hour and stop it, mid-air, without destroying it, without dropping it, without even denting it? It's a question that sounds like it belongs in a superhero movie, not an engineering meeting. Yet right now, on a wind-swept beach in Boca Chica, Texas, SpaceX has built a machine that does exactly this, and they've made it look easy. The answer to this impossible question stands 146 meters tall, weighs more than 1,000 tons, and has arms that could cradle a building. They call it Mechazilla, a name that started as a joke in an Elon Musk tweet, but has become deadly serious engineering reality. This isn't just a launch tower that happens to catch rockets. It's a robotic giant with chopstick arms that can pluck the world's most powerful rocket booster out of thin air with the precision of a surgeon and the strength of a titan. The entire structure cost less than a single space shuttle launch, yet it's designed to catch hundreds of rockets over decades of operation. And here's the part that will really blow your mind. For all its revolutionary audacity, the actual catching mechanism is probably simpler than the suspension in your car. That's the paradox we need to unpack. How something that looks impossibly complex, that does something never before achieved in aerospace history, actually works on principles so simple that a high school physics student could understand them. The magic isn't in exotic materials or breakthrough technologies. It's in having the courage to ignore 70 years of aerospace convention and ask a question so basic it sounds naive. Why does a rocket need to land at all? To understand Mechazilla, you first have to understand the almost religious philosophy that drives every decision at SpaceX. First principles thinking. It's a mental model borrowed from physics, popularized by Aristotle, and weaponized by Elon Musk to destroy entire industries. The concept is deceptively simple. Strip away every assumption, every convention, every "that's how it's always been done," and rebuild from only the fundamental truths that cannot be reduced further. When SpaceX applied this thinking to rocket landing, they didn't ask, "How do we land a rocket better?" They asked, "What is the absolute minimum required to transition a rocket from flight to ground?" The answer changed everything. Every rocket that has ever landed, from the Apollo lunar module to SpaceX's own Falcon 9, has carried its landing system with it. Legs, struts, shock absorbers, deployment mechanisms, all dead weight for 99% of the mission, only used in the final seconds. The Falcon 9's landing legs alone weigh 2,000 kilograms. That's 2 tons of payload capacity sacrificed just to touch down. On Starship, scaled up to handle a 250-ton booster, landing legs would weigh at least 10 tons. That's 10 tons that could have been cargo, fuel, or simply not built at all. But the weight is just the beginning of the problem. Landing legs create what engineers call an inefficiency cascade. First, there's the manufacturing. Each set of legs requires specialized materials: titanium, carbon fiber, precision hydraulics, and deployment mechanisms that must work perfectly after being exposed to the violence of launch and the temperature extremes of space. That's millions of dollars per booster. Then there's integration. Legs must be attached, tested, and validated before every flight, adding days to the turnaround time. After landing, they must be inspected for damage, retracted, and serviced. SpaceX's own data showed that landing leg refurbishment was consuming 30% of the total time between Falcon 9 flights. For a company trying to make rockets as reusable as airplanes, this was unacceptable. The legs had to go. The breakthrough came during a 2020 design review that has since become SpaceX legend. The team was struggling with Super Heavy's landing leg design. The mechanisms were becoming so complex They looked like mechanical spiders. An engineer, stories vary on who, asked the forbidden question, "What if it doesn't land at all? What if we catch it?" The room went silent. It was absurd. You don't catch rockets. Except, why not? If the tower is already there, already strong enough to support the rocket, already equipped with mechanisms to move and position massive loads, why not use it? The rocket doesn't care if it's standing on legs or hanging from arms, as long as it's stable and can be refueled. Elon Musk announced this insane plan the way he announces everything, with a tweet that sounded like a joke. August 30th, 2021. SpaceX will try to catch the largest ever flying object with robot chopsticks. He included a clip from The Karate Kid, where Mr. Miyagi catches a fly with chopsticks, saying, "Man who catch fly with chopstick, accomplish anything." The aerospace establishment thought he'd finally lost it. Catching a rocket with mechanical arms wasn't just unprecedented. It seemed to violate the fundamental philosophy of aerospace engineering, which prioritizes redundancy and independence. What if the arms fail? What if the tower is damaged? You've lost not just your landing capability, but your launch capability too. Boeing executives were reportedly laughing in their boardrooms. They're not laughing now. Let's talk about what SpaceX actually built. The Launch and Catch Tower. Officially designated Stage 0 because SpaceX considers it as important as the rocket itself, rises 146 meters into the Texas sky, taller than the Statue of Liberty on its pedestal. The frame consists of 4 massive vertical columns, each 1 meter in diameter, connected by a triangulated web of steel beams that would look at home on a suspension bridge. The entire structure weighs over 1,000 tons and is anchored to a foundation that extends 30 meters underground, deep enough to hit the water table. This isn't just built strong. It's built to withstand hurricane-force winds while holding a fully fueled Starship stack that weighs 5,000 tons. The catching arms, the chopsticks, are engineering poetry in steel. Each arm is 36 meters long, longer than a basketball court, and weighs 120 tons. They're not simple beams, but complex mechanisms containing hydraulic actuators, power systems, and sensor arrays. The arms can open to a span of 40 meters and close to less than 9 meters, precise enough to thread a needle if that needle were the size of a rocket. They move on a carriage system that can lift them at 2 meters per second, seemingly slow until you realize they're lifting the equivalent of 2 blue whales at the speed of a fast walk. The positioning accuracy is plus 10 centimeters over their entire range of motion, achieved through a combination of laser ranging, GPS, and computer vision that tracks targets painted on the booster. Here's a detail that perfectly captures SpaceX's approach. The main lifting mechanisms for Mechazilla weren't purpose-built, they were salvaged. Back in 2020, when SpaceX still planned to launch Starship from ocean platforms, they bought 2 deep-sea oil rigs named Phobos and Deimos, after Mars's moons. Each rig came with a drawworks system, the massive winch mechanism used to lower drill strings thousands of meters into the ocean floor. These drawworks, designed to handle 500-ton loads in hurricane conditions, were perfect for Mechazilla. When the ocean launch plan was scrapped, SpaceX stripped the drawworks from the rigs and installed them in the tower. A mechanism designed to drill for oil is now catching rockets. That's first principles thinking. Use what works, regardless of its origin. Now, let's get into the physics of the catch itself, because this is where conventional thinking said it was impossible. The Super Heavy booster returning from space isn't just falling. It's a 250-ton projectile traveling at 65 meters per second, 145 km/h, just seconds before the catch. The rocket engines slow its descent to nearly zero vertical velocity at the catch point. But here's the problem nobody talks about: horizontal velocity. Wind, atmospheric perturbations, and control uncertainties mean the booster is always drifting sideways at 2 to 3 meters per second. That might sound slow, but imagine trying to catch a building that's sliding sideways at walking speed. The momentum, mass times velocity, is enormous. It's like trying to stop a freight train with your hands. Let's put numbers to this. A 250-ton booster moving laterally at 3 meters per second carries 750,000 joules of kinetic energy. For comparison, that's equivalent to a car traveling at 170 miles per hour. This energy has to go somewhere in the fraction of a second between contact and capture. If the arms were rigid, the impact force would be around 2 million newtons, enough to crumple the booster like a beer can. SpaceX needed a way to absorb this energy gradually, turning a collision into a caress. The solution they developed is so elegant it seems obvious in retrospect, yet no one had ever tried it at this scale. The catch happens in 3 distinct phases, each lasting fractions of a second, but engineered with microscopic precision. Phase 1. Initial contact. The booster has 2 hardpoints, reinforced catch pins, located just below its grid fins. As the booster descends, these pins must align with rails on the chopstick arms within a tolerance of 10 centimeters. The rails are lined with a specialized foam-backed steel surface that looks solid but is designed to deform. When the pins make contact, this surface dents inward by up to 5 centimeters, absorbing the initial shock like a catcher's mitt receiving a fastball. The foam has a carefully tuned compression curve, soft enough to prevent damage, firm enough to provide control. Phase 2. The embrace. Within 200 milliseconds of contact, the deformation of the foam triggers pressure sensors that activate the hugging sequence. The chopstick arms, which were stationary, begin moving inward at 0.5 meters per second, matching and then exceeding the booster's lateral motion. This is crucial. By moving with the booster rather than against it, the arms avoid creating opposing forces that could cause structural damage. Simultaneously, the foam continues to compress, increasing its resistance in a controlled manner. The booster, instead of slamming to a stop, is gradually enveloped. Engineers describe it as catching an egg with a pillow that turns into a firm mattress. Phase 3. Weight transfer. This is the moment of truth. The booster's engines shut down, and 250 tons of rocket need to be supported instantly. Hidden within each chopstick arm are arrays of hydraulic pistons and gas shock absorbers, essentially massive versions of your car's suspension, but engineered to handle forces that would flatten a building. As the booster's weight transfers to the arms, these systems compress, allowing the entire catching rail to drop by up to 1 meter. This drop is precisely controlled. Too fast, and the booster experiences damaging G-forces. Too slow, and the momentum isn't absorbed. The hydraulic system uses 20,000 psi of pressure, managed by valves that can adjust flow rates 100 times per second. The result? The booster decelerates from its residual velocity to complete rest in 1.5 seconds, experiencing no more than 2 Gs, gentle enough that if there were astronauts aboard, they'd barely spill their coffee. None of this would be possible without the computational orchestra conducting the catch. The tower runs custom software that processes data from 200 sensors 1,000 times per second. Laser rangefinders track the booster's approach from 1 kilometer away. Accelerometers in the arms detect contact within microseconds. Pressure sensors in the hydraulics adjust dampening in real time. Machine learning algorithms, trained on thousands of simulated catches, predict the booster's trajectory and pre-position the arms. The entire system can abort the catch and command the booster to divert to an ocean landing up to 3 seconds before contact. It's not just catching a rocket. It's a dance between two robots, choreographed by artificial intelligence. What we're seeing today is version 3.2 of the catching mechanism. Version 1.0, tested with mass simulators in 2022, failed catastrophically. The arms couldn't respond fast enough, and the test article was damaged. Version 2.0 worked, but required the booster to hover for 2 seconds, burning precious fuel. Version 3.0, first used successfully in October 2024, proved the concept, but showed excessive wear on the foam pads. The current version incorporates lessons from 14 test catches, 3 near misses, and 1 spectacular failure that SpaceX, in typical fashion, posted online with the caption, "Learning Opportunity." Each iteration has reduced the catch time by seconds and the stress on the booster by percentage points, approaching the theoretical optimum calculated by physics simulations. The real genius of Mechazilla isn't technical, it's economic. Traditional rocket landing systems cost $5 to $10 million per vehicle in hardware alone. Refurbishment after each landing adds another $2 to $3 million. Turnaround time is measured in weeks. Mechazilla's operational cost per catch? About $50,000, mostly in foam pad replacement and hydraulic fluid. Turnaround time? SpaceX is targeting 1 hour from catch to ready for launch. This isn't just an improvement, it's a paradigm shift. At these economics, launching a rocket becomes comparable to flying a large aircraft. The space economy doesn't just grow, it explodes. Satellites become cheap enough for startups, space hotels become economically viable, Mars colonies become possible. In the end, Mechazilla proved something profound about innovation. The biggest breakthroughs don't always come from inventing new technologies. Sometimes they come from having the courage to ignore what everyone knows is true. Every aerospace engineer knew that rockets needed landing legs. Every safety officer knew that catching a rocket was too dangerous. Every accountant knew that building a giant robot tower was too expensive. SpaceX ignored them all and built something that works, not despite its simplicity, but because of it. Mechazilla doesn't use any technology that didn't exist 20 years ago. There's no exotic materials, no quantum computers, no breakthrough physics, just steel, hydraulics, foam, and the audacity to catch a falling skyscraper.